So this is a reminder, Class Connect sessions are recorded and distributed for learning purposes that are listed here. As always, be respectful, appropriate, and participate, but please don't share personal information during the class for your own security reasons. We are in the February 26th attendance ticket. If you missed it, it is in the chat box. Link is there for you along with the password. I do need green checks from everyone, letting me know you've got it ready to go. Remember, I do always recommend, even if it's working for you, definitely write down the password because you never know. Wi-Fi and technology always tend to go a little bit crazy. So write down the password somewhere, have it. I just make a list. Just make a list of the passwords. Looking good. Yes, exactly. Skynet, right? All right, cool. Let's go ahead and get started. So we are on day 20. Look at this, guys. We are officially in the 20s. All right, so that means that in 2.5 days, we will be halfway through quarter number 3. Oh my gosh. And take a look at this. In 2 days, you do have your midterm exam, so it's pretty much halfway in between. So that should make sense. So today we are working on our lab. So we're going to design a thermos. We're going to look at some different materials. And that's what we're going to do today. It's actually your easiest lab, and it does not require any Google things. So it's really nice because you don't have to do like Google Sheets or Google Drawings or anything. So give me a smiley face if that makes you happy. Makes me happy too. It actually makes it easier to grade. Yes, I know. That's exciting. Yeah, it's super, super easy. So you definitely want to make sure you get this done. It is 10% of your grade. 10% of your grade. Cool. Tomorrow we do have a game day to review Unit 5. Again, that review should help us out on Thursday when we do our midterm exam. Remember, if you attend class, the midterm exam is really not that bad because I go through every question with you. But make sure you attend class. Make sure you work on it with me. And then Friday, we'll be starting unit number 6. There's only 9 units, and we're already in unit 6. Oh my goodness. So we have been talking about energy. We talked about potential and kinetic energy. We talked about heat energy really in depth. And now we're going to go ahead and start applying it. So, okay, yep, no worries, Caleb. Yeah, definitely email me, and I can make sure that you're all set up for the midterm on Thursday, okay? Today we should be able to describe how heat moves by conduction. We've actually already learned that, so we're just going to review it. We should again be able to explain the differences between conductors and insulators. Again, a quick review because it's related to our topic to today. And we should be able to determine ideal materials for an insulated thermos. So that is where we are going today. All right, let's do some quick review. Remember, the word kinetic means what? Tell me in the chat box. Everybody should know this by now. We talk about this word all the time. What does the word kinetic mean? Yes, it means movement. It means to move. It means motion, right? So kinetic theory means the motion of particles. And what this means is we believe that the motion of particles is what causes heat. So the hotter objects are, the faster they move. The colder objects are, the slower they move. And we saw a great demo of this yesterday, right? Hot water, cold water, and warm water. And we put food dye in them. And in which glass of water did the food dye spread out the most or the quickest? In the hot, warm, or cold glass? Yeah, exactly. So we actually saw the dye move really, really quickly. So those particles in the hot water were just swimming around so fast that they were able to mix the dye up super quickly. Whereas in the cold glass, it just kind of stayed still and you could see the swirl starting, but it took a really, really long time, right? Now, quick reminder that the conservation of energy, you'll hear this a lot, this idea of conservation in physics. Conservation of energy says energy is never created nor destroyed, right? The total amount in the universe is the same always. So even if you say, oh, the house is losing heat, that's not really true because heat energy is never lost. It just changes or moves. And specifically, one of the way it moves is through conduction. So this was the first way that we move that heat moves. First way that we learned that heat moves, which is when objects are touching, the molecules will collide from one object to the other object and transfer that heat. And remember, things always move from hot to cold, right? Because is cold a real thing? Tell me in the chat box, is cold a real thing? No, it's not. Cold, again, is just the absence of heat. So you can't go from cold to hot because cold doesn't actually exist. You can only go from hot to not hot. Smiley faces if all this makes sense. Again, this was a quick review. You can see a picture of conduction here. Again, conduction requires touching the object. Excellent. So that is definitely where we are going today. So reminder that conductors help to speed up the transfer of heat, which should make sense, right? What word do you see in conductor? Yes, exactly, Tariq. You can really peeve off your friends by being like, no, you're feeling the absence of heat. I'm sure they'll love you for that. All right, tell me in the chat box, what word do you see in conductor? That should be familiar. Yeah, right, conduct, which was also the same word in conduction. So logically enough, conductors are good at conduction. Smiley faces if that makes sense. They're good at conducting heat. All right, so they're good at transferring this heat. They speed up the transfer of heat. Now, insulators, on the other hand, just like when you are insulated in the winter and you're wearing an insulated jacket, that helps you to not lose your heat as quickly. So they slow down the transfer of heat. They prevent you from losing heat. Now, remember, they don't stop it completely, right? Your coat, while effective, if you stand outside in the cold forever, you will eventually get cold. Smiley faces if that makes sense. You will eventually get cold. Right, your jacket can only do so much. Right, and the reason for this is because insulators don't stop heat completely. That's impossible. Heat will always move, but they are able to slow it down at least a little bit. Okay, so remember, insulators are things like wood and rubber, and conductors are things like metals. So take a look over here at this pan. We've got 2 ice cubes here. What do you notice are the differences between the left one and the right one? Tell me in the chat box, what differences do you notice between the left one and the right one? Go ahead, write in the chat box. Okay, no worries. Thank you, Dorian. Yeah, the left one is melting, the right one is not melting. And what do you notice, what else do you notice is different between them? So one of them's melting, the other one is not. Yes, the one on the right is sitting on foil, right? So the interesting thing here is that they're both kind of on metal. Right, so this one is a metal pan, this one is aluminum on a metal pan, right? However, okay, if this is a hot plate, meaning that it's getting heat from underneath, which one has less layers between it and the heat? Which one has less layers? The one on the left, right? So the same thing is true with conductors, right? Insulators will always eventually transfer heat, but conductors aren't perfect at conducting heat. Even a conductor like foil, right, will still be a little bit slower than it being on the direct flame. Smiley faces if that makes sense. It's still going to be a little bit slower than if ice was just directly on the flame. Okay, Michaela, it looks like your computer's lagging, so you can try. All right, cool. All right, so let's go ahead and make sure that this, oh, okay, good. Let's go ahead and make sure that this makes sense. So on the whiteboard, what I want you to do, grab your whiteboard tools, grab the box or circle tool, and I want you to circle the correct terms. So conductors, do they slow down or speed up transfer of heat? Insulators, slow down, speed up transfer of heat. And which way does heat move, hot to cold or cold to hot? Go ahead and circle the correct answers on the whiteboard. Go, go, go. Take about 10 more seconds. Seeing lots of good stuff up there. All right, perfect. Let's go ahead. I'm going to pause your tools. Sorry, I know if you were still drawing, I cut you off, but I want to make sure that we get to all of this. So let's take a look at this. So first off, you said conductors speed up the transfer of heat, and that is absolutely correct. Let me go ahead and grab my tool. So conductors speed up the transfer of heat, correct? And therefore, insulators are the opposite. They slow down the transfer of heat. Can an insulator completely stop the transfer of heat? Tell me in the chat box, can we completely stop the transfer of heat? Is that possible? No, we can't completely stop it. It just slows it down. And you guys are correct. Heat moves from hot to cold because cold is not a real thing. Cold is just the absence of heat. All right, go ahead. This is number 1 in your ticket. Please go ahead and match these up correctly. You have 30 seconds. I'll give you 40 seconds. Green checks when you have number 1 saved. Go, go, go. All right, just waiting on a few more green checks. Amir, Tony, Bradley, Danny, Dusty, Edwin, Jaime, Jackie, Caleb, Martina, Maxine, Mel, Michael, and Blossom. Just want to make sure you are all on board. Thank you, Danny. Awesome. Looking good, looking good. All right, let's go ahead and keep on going. Here we go. So here's what our lab is going over today. So we're going to take a look at what types of materials influence heat transfer. So we're going to be taking a look at a couple different materials. We're going to see which ones will speed up heat transfer, like conductors, and which ones will slow down heat transfer, insulators, right? And then we're going to apply that and figure out what materials would be good to go into a thermos. All right? So that being said, how many of you know what a thermos is? How many of you have ever seen one of these before? Right? Maybe you have one. I do have one somewhere in the house, but I'm not really sure where it is right now. Yeah, awesome. So thermoses are great. And why are they great? Tell me in the chat box. What do you use your thermos for? Or if you ever see like camping videos, what do people always use thermoses for? Yeah, they hold heat. So specifically what kind of, yeah, it keeps your water hot, keeps your coffee hot, right? Keeps hot chocolate hot. If you have soup during the day, it keeps your soup hot, right? Now, the cool thing is though, thermoses can also work the opposite direction. How many of you have ever put a cold drink into a thermos? How many of you have ever put a cold drink? Yes. So thermoses are also great because they can actually keep cold things cold for a long time too. All right. So actually, they can actually keep things colder, I think, for longer. I don't know if that, I think that's true. So like, for example, my thermos that I have can keep hot things hot for 24 hours and cold things cold for 48 hours. Okay, I'm pretty sure that's which one it is. But here's the thing, guys. No matter what, the thermos is working because it's made of insulated materials, which means that heat can't get in and heat can't escape, which works either way, right? If you have hot liquid, right, it's preventing the heat from the hot liquid from getting out. And if you have a cold liquid, it prevents heat from the environment getting in and warming up your drink, because warm lemonade is disgusting, right? Smiley faces, everyone, if that makes sense. I don't know anything you just wrote, Tariq. I have no idea what any of that means. Cool. All right, so thermos is made of materials that help to insulate it, slowing down the transfer of heat. So our experiment's going to take a look at what materials are good at insulating that we could use in a thermos, okay? So what I want you to notice is, right, we know thermoses, right? But I also want you to notice this over here. What is this on the right? Yeah, warm lemonade would be super weird. What do you see here on the right? What is this? I'm sure this is familiar. This is actually my favorite kind of bottle. Go ahead, tell me in the chat box. All right, we got the thermos on the left. What's on the right? What goes in this? Sports, exercise, every day. Yeah, it's just a water bottle, right? But the thing about this one on the right is this one is actually an insulated water bottle. So take a look at this. What do you notice is kind of different about this water bottle? Look really closely at this water bottle. What do you notice is a little bit different than everyday water bottles that you might see? Again, this one is considered insulated. Yes, yeah. So, I mean, the straw is interesting. I definitely like these straws. They're called bite valves, so you actually have to bite them in order to get them to work, which is actually interesting because psychologically people like to bite stuff, and so it actually makes you drink more water. But yeah, the part I'm actually talking about here is it has two layers. Smiley faces if you see that. It's got this dark blue layer and this light blue layer. Cool, yes. And what happens here is we've got this light blue layer, but what do you think is happening in between the two layers? What is in between the two layers? Yeah, it could be air. It could actually also be the absence of air. There could also be a vacuum in between those, okay? Now, the interesting part about this is, remember, when we have close molecules, they will conduct heat much faster, right? So solid things conduct heat very quickly, whereas liquids and gases conduct heat much more slowly because there's less molecules to transfer that heat. So the less molecules you have, the better it is at insulating, right? So inside here, where there's air, or possibly not even any air, possibly just a vacuum, there's a lot less molecules, and so it is really, really good at insulating and keeping your water cold. Smiley faces if that makes sense. Smiley faces if that makes sense. Okay. I would have to do more research. It's possible that inside of thermoses there's also a layer of gas or of a vacuum, but that would also be really great because, again, gases and vacuums are really great at insulating. Oh, no. I'm glad you feel successful, Tariq. Cool. All right, so this is going to lead us to our virtual lab, okay? So we still have the virtual lab component, but again, this is a super, super easy one. So I'm going to go ahead and I'm going to send you the link to the virtual lab so that you can kind of take a look at it at the same time that I am. Okay, if your computer slows down too much, don't worry, you don't have to open it up right now. You can do it later, okay? So if you know your computer is too slow to handle that, just don't worry about it. But if you want to open it up, you can open it up right now. Okay, smiley faces, everyone, if you understand. Have it open, don't have it open, either way, it's not going to affect you. Okay, awesome. Okay. So this is going to be a virtual lab. I know, I love labs too. And you do need to gather your own data for this lab. So the data is not provided. You need to actually get your own data for it. Again, the link to the virtual lab is going to be in question number 1. Thumbs up for those of you that opened it. Thumbs up if you can see that. In number 1, you can see the link to the virtual lab. Okay, I can actually show it to you right here. So here's question 1, follow the instructions. Click here, link to heat transfer virtual lab. Cool. All right. So this is what the virtual lab is going to look like. It's going to have 5 different materials that you're going to be testing: aluminum, glass, fiberglass, air between glass, and brick. It has a hot plate, which, what do you know, gets hot when you turn it on. It has a timer right here because you're going to be timing how long it takes for ice to melt on these different materials. It has some tongs or tweezers so that you can pick things up and not contaminate them with your dirty hands. Your dirty virtual hands, I guess. And then we have some ice over here in the bucket, okay? Keep in mind that this does use Adobe Flash Player. So if you get either of these things, it's super easy. So if you get this warning right here, literally just click anywhere here and then allow your browser to use Adobe Flash and it'll work. If you get this one over here, it's a little bit trickier. Don't click the red button. The red button doesn't lead you anywhere. Instead, click right above it where it says Activate Adobe Flash. It doesn't look like a button, but it is in fact a button, right? So right here, you guys can see this where it says Activate Adobe Flash. That is actually a real button, okay? Smiley faces if you understand, confusion faces if you don't. Again, most people don't run into these issues, but I want to make sure if you're having any issues opening the virtual lab, there's no excuses. I know every trick in the book, so there's no excuses. Cool. All right. So what we're going to do is I am actually going to show you the instructions live. So I know for a lot of labs we do a recording, but because this is a super short and sweet lab, I'm actually going to do it for you live. But here's the deal. I want you guys to at least wait and watch me do the instructions. Okay, so watch all of the instructions, and then when I'm finished, you can go ahead and do it yourself, okay? Because if you try to do it at the same time as me and you get distracted and you miss something, then I have like 500 people in the chat box being like, wait, what'd you do? What'd you do? I missed it. And then people feel frustrated because you're not paying attention, and you feel frustrated because you missed something, okay? No, you should not get the same answers. You should not get the same answers, okay? So yeah, so that being said, I'm going to show you how to do it, but don't copy my data because, again, you should not end up with the same data as me, okay? Thumbs up if you understand. You're going to watch completely without putting your mouse on the lab on your side, and then when I'm finished, you can do it yourself. Okay, Miss Hale, I can help you in a few moments figuring that out, okay? Again, if it's either of these issues, right, Adobe Flash, click here. Or if it says right here, you get the red button, don't click the red button, click where it says Activate Adobe Flash. Okay, let me know if either of those work, otherwise I can troubleshoot some more with you in a little bit. Okay, so again, don't copy my example. So let me go ahead, I'm going to share this with you. All right, can everyone see my screen here? Perfect. All right, here we go. Let's preview this. Looking good. Again, it's super easy, so we still have plenty of time. Cool. Okay, so this is what the lab looks like, all right? So hopefully this link should work now. I did update it. So if you click on that, hopefully it now works. I don't know why it's being silly right now, but hopefully it works in the future. I'll troubleshoot that some more. But again, if you need the link, here it is. All right, so here's that link again. Okay, cool. So what we're going to do, you can go ahead and you can click Begin the Lab, grab your gloves, right? Sorry, again, just watch my instructions first. Yeah, right click and open a new tab. All right, so here again, this is what you can see. So you can see all of your materials here. You can see the hot plate, the tweezers, the timer, and the ice right here. Okay, so what you're going to be doing is you're going to be trying to figure out how long it takes for ice to melt on each of these different materials. All right, so the results are going to be in the form of minutes, seconds, and milliseconds. Okay, so you can see that right here on our timer. The first 2 digits are minutes, the second 2 are seconds, and the third ones are milliseconds. Smiley faces if that makes sense. Okay, again, I did write it right here, so minutes, seconds, milliseconds. Okay, that way it's super obvious. Cool, all right. So what you're gonna do is you're gonna grab your first material. So in order to grab your materials, you do need to be holding the tweezers. So you grab the tweezers by clicking on them, and then a single click on the material to grab the material, and then a single click to drop it onto the hot plate. All right, and you can then go over here to the ice, grab one piece of ice, and drop it on top of the material, which in this case is the aluminum. All right, again, single clicks all around to pick up and drop off. How do we feel about that? Smiley faces if that makes sense. Okay, did I lose anybody right then? Hopefully I didn't. That's the easy part. Cool. Then what we do is we're going to go ahead and we are going to turn on the hot plate. All right, so here's the button to turn it on. And at the same time, you're going to then start the timer. All right, so we're going to turn on the hot plate and then start the timer. Okay, and you'll see that your ice begins to melt. So you're going to wait for the ice to melt. Go, go, go. And as soon as the ice is completely gone, I'm going to click stop. Get ready for it. Ready for it. And stop. All right, so here's what I had. I had 0 minutes, 19 seconds, and 29 milliseconds. Again, yours should be different. You should not end up with the same data as me. So don't type my data, okay? So for me, though, I would put in here 0, 0. What did I say? 19 seconds, and 29 milliseconds. Okay, thumbs up if you feel good about that. Okay, so it's super easy. You just figure out how long it takes to melt. Again, minutes, then seconds, then milliseconds. Cool. So I'll do one more just in case. All right, anyone feels uncomfortable. So in order to reset this, turn off the hot plate, click reset on your timer, grab your tongs, and that'll allow you to pick up the aluminum. So you'll pick up the aluminum, drop it back where it belongs, grab the glass, all right, and drop that on top of here. Okay. So then, once more, make sure your hot plate is off. So then go grab a new piece of ice, drop it on here. Again, making sure your hot plate is off. Yeah, it's just 1 cube every time, just a single cube. And then you're going to turn on the hot plate here and press start, okay? And again, we can see that it begins to shrink. It does begin to melt. Is this one melting as quickly as it did on the aluminum? No, it's definitely not. It's definitely taking a little bit longer, right? So it does take a little bit longer on some of the materials. None of them take super long though, so don't worry, you're not going to just be sitting here forever. There are a couple of them that take like a minute or so though, so keep that in mind. There's a little bit of wait time, but still not really bad. All right, so let it go, let it go. Oh, frozen. I did that unintentionally, but now I'm really proud of myself. All right, so let it continue melting until it's almost done, almost done. Get ready to stop the timer. This one takes so long. I should use a different material next time. I know which ones are the fastest. All right, here we go. Give it a couple more seconds. I know, exactly. A minute feels like forever in our technology age. With our Vines and TikToks, right? All right, here we go. Almost gone. Get ready to stop it. Oh my gosh. Keep going, ice. You can do it. It's still got like that little centerpiece right there. Cool. All right, well, I'm going to go ahead and stop it. There we go. So it stopped. Yeah, I think it disappears when it completely is melted. So just wait till it disappears, basically. All right, so that was 1 minute, 23 seconds, and 46 milliseconds. So I come back over here, type 01. What was my seconds? 23. And my milliseconds was 46. Okay, so super easy. You just do that for the remaining ones as well. Okay, so again, your data should not look like mine. Don't use my data. Okay, so don't use my data. Don't copy. Okay, smiley faces if you feel good about that. Confusion faces if you need help with any of that. Again, it's a super simple lab, and there's no Google stuff involved. No Google sheets or anything. Cool. So then what you're going to do is you're going to go ahead and take a look at all of your results, and you're going to order them from the least insulating to the most insulating. Now let's think about this. Thinking about insulation, helps to prevent heat transfer, do you think the ones with lots of time or little time are better insulators? Okay. Yeah, so then you do the remaining 3. So tell me in the chat box, which ones are better insulators? The ones that melt really quickly or the ones that take a long time to melt? Think about your thermos, all right? Which one is going to be a better insulator? The ones that take a long time, right? So this is really important, okay? I'm going to type this right here, okay? So the ones that take a long time are better insulators, okay? Because they take longer to do heat transfer. Okay, so it takes much longer for the ice to melt. If it's a short time, then those are going to be worse insulators, okay? Because they take shorter time to do heat transfer, okay? So that being said, we currently only know aluminum and glass, but aluminum, would I mark that as one of my least insulating or most insulating? It has a short time, so would I mark aluminum as a least insulating or most insulating material? Yeah, it would definitely be much less insulating because it melts super fast, right? Short time means it's a worse insulator. So aluminum might be like number 1 or number 2, right? So it might be number 1, might be number 2. Don't copy this because obviously we don't have all of our data. And then glass, do you think that would be more on the side of a least insulating or most insulating? What do you think glass would be? Least insulating, most insulating? Yeah, probably more insulating because it took much longer, right? So it took a longer time. It's a better time, better insulator, prevents things from melting, right? So this one might be 3, 4, 5, right? So again, we don't know for sure because we don't know the other data, but these are examples. Okay, smiley faces if that makes sense. Smiley faces if that makes sense. Okay, again, this will be in the recording. If you want, you can take a quick picture of this or write it down somewhere. But again, long time, better insulator, short time, worse insulator. Okay, cool. Now the very last question, you should be pretty familiar with this. I do have the question already typed out for you. So the last question tells me, which 2 materials do you think would be best for putting in an insulated container? So that means taking a look at your data up here, which again, we don't know yet. But once we look up here, we're going to find the 2 most insulating materials, which means number 4 and number 5. So you're finding material number 4 and material number 5. Smiley faces if that makes sense. Right? Because those are the 2 most insulating, 4 and 5. All right, cool. So you would take 4 and 5, and those would be your 2 materials. So you would say, my first material would be whatever you marked as number 4. Okay, give me the actual result because we should always include data in our recording, right? So we would include our actual time. So maybe 1, 23, 46, depends on which material is the most insulating. So minutes, seconds, milliseconds. And then tell me, what did it take a short or long time to be a good insulator, right? Which we already actually should know this. Which ones should be a good insulator? It takes a short time to melt or a long time to melt? Tell me in the chat box, which one would be the good insulator? Yes, it should be long. So no matter what, everybody should have the same answer here, that this one takes the long time. Same thing with down here. Your 2 best insulators are going to take a long time for the ice to melt. Thumbs up if that makes sense. Again, we're using material 4 and material 5 from what we ordered up here. Okay. Again, up here you should be going from shortest to longest, least insulating to most insulating. All right. So super easy lab, right? Should be able to knock it out of the park really quickly. I'm sure some of you are already ahead of the game and already doing it, even though I told you not to. Cool. All right, looking good. So let me go ahead and jump back over here. All right, do we have any questions? Tell me in the chat box. Any questions? Any questions about that? All right, awesome. Well, I look forward to seeing your labs. I do have some instructions here, right? So use your tongs to place the material on, then place the ice cube, turn the hot plate on, start the timer, wait for the ice to melt, stop the timer, record it in your table, turn off the hot plate, remove the material, repeat. Okay, so those are some basic instructions. Again, these will be in the recording, the 5D recording once we're done with class. Okay, so if you need to look at the instructions, I have them right here for you. Okay. Yeah, sure. Sorry. I thought I put the, maybe I put a different link in there. Sorry. So here is the link to the attendance ticket. Tongs is a funny word. Cool. All right. And again, here's question 2 and question 3. Easy peasy. Let me go ahead and remind you that the lab is technically due at 4 o'clock. It is a fast lab, so I'm sure many of you will get it done by then. But remember, I really don't grade them until the weekend. So just take your time, do it correctly. I care more about it being correct than it being in by exactly 4 o'clock, because you can turn things in late and still get full credit. So do it correctly. Don't turn something in blank. That frustrates me so much. So just do it correctly. Okay? Here's your last word. Thanks so much, everyone, and I will see you later. Have a wonderful day. Bye.